Hello and welcome everyone. We are really happy to have you all here this evening for a session full of action-packed learning. I am Priyanka, a part of the data science team of Analytics Vidya, and I'll be the moderator of this session. My colleague Anand will be helping you with any queries that you will be having. And so, for those who have joined us for the first time, a brief introduction to the DataHour session. The DataHour is a series of webinars conducted by Analytics Vidya and led by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding to our community members. I hope you are excited to attend this data hour with us. And before we kickstart things, I will just help you with a quick recap of the housekeeping items. We are recording the session and we will make the recording available in few days on our YouTube channel. Please use the Q&A section for asking any questions you might have during the session, and we will do our best to answer them as the data hour progresses or towards the end. Also, we will share a poll about the feedback towards the end of the session, which I request you all to kindly fill up. Now, on to our session today, which is Energy Data Science Project from Scratch. In this data hour, you will get a good sneak peek into what kind of data processing and projects happen in the oil and energy sector. You will gain an understanding of raw data from an oil producing field, that is the oil well data, as well as the water injector well data. We will talk about null handling, feature engineering, outlier detection, descriptive statistics, etc. At the end, introductory machine learning will be explained to conclude the session. And now, on to our speaker in this session of Data Hour. We have Divyanshu Vyas with us. He is the energy data scientist and founder at Petroleum from Scratch. Divyanshu is a machine learning and data science consultant at Oil and Energy Projects and a community member for Python and data sciences for the energy industry with the motto to be the perfect mix of physics and mathematics. Over to you, Divyanshu. The virtual stage is all yours.
Thank you for that introduction. Thank you everyone for joining in. We really don't have too much time, and I'm expecting that a lot of you are from the domain which not from the domain which I'm from. So I come from the petroleum engineering domain. I come from the oil and gas industry, and I'm exploring the various opportunities that lie in the intersection of the data sciences with the oil and gas industry, the various problems that can be solved using various machine learning algorithms for the oil and gas industry. And with the experience that I've had, I've realized that the boom is just very new, and a lot of more opportunities are growing as we step into this in this industry. And as far as I can look at it, the energy industry has been a bit slow to adapt to the data revolution, and which is again a blessing in disguise for someone who wants to get into the data science industry. If energy industry fascinates you, oil and gas, electric vehicles, all these things, they fascinate you, this is a good market to start your leg in. So I'll share my screen. Let me know once it is visible, and we will start things. I saw the poll. I saw that a lot of people are new to the data science industry, and some of them are really experienced. So I hope the session brings good light to both kind of audiences. For those who are well versed with data sciences, maybe an introduction to a typical oil and gas project can help. For those who do not know either of them, I mean, I hope this becomes a good session to start with. So I'll share my screen. Let me know once you can see it. Good to see some people from oil and gas industry. Sharing my screen. Let me know once you can see it.
Sure.
Yeah. Can you see my screen? All right. Thank you. Okay, so basically, let's just start with the typical possibilities. What happens in the oil and gas industry? A quick 2-minute introduction about what basically it is all about for a layman. So, as the part of the industry, there are various teams that work in. Our basic aim is to figure out what rock has oil in it, and how can we extract oil from like thousands of feet downwards in the most efficient manner. So if you just imagine that a piece of rock has oil in its pores, it does not just give away oil, right? We have to carry out a lot of things in order to extract as much oil as possible from and the problem is that rock is lying thousands of feet below the surface. So there is a team of geologists and geophysicists. They work together in order to build a simulation, a static simulation of the entire we call it the subsurface, which is a layer of rocks above which you are standing, and the various signatures tell us that where oil can be possibly located. And then we as oil and gas maybe drilling engineers, we drill holes up to that point, and our aim is to extract oil from the hole which is drilled. Now the problem is that initially, at least let's say 5 to 10% of oil will just flow onto the surface because of the pressure that it has in the reservoir, right? We call it the reservoir. Whenever I use the word reservoir, I'm just talking about the rock which is containing oil lying thousands of feet below us, right? Now some of the oil will just flow up because it has a lot of pressure, and you just open up a vent. It's almost as if you open up a Coca-Cola bottle and the fluid just starts popping out because it has a lot of pressure. But slowly it keeps on dying. The pressure, the flow of the fluid, it keeps on dying, right? And then we need to use a lot of other ways to keep on pushing the oil to the surface. We drill other wells through which we inject some water. We drill some other wells through which we inject some surfactant, the detergents and all, so that the oil feels easier to move. So we try a lot of things, and that totally sums up the entire oil and gas industry. And I'm not using any terminologies that is hard for a non oil and gas engineer to understand, but this is the entire value chain. And then once the oil comes up to the surface, we try to refine it, we try to extract the usual components out of it, and then we try to transport it, which is called the downstream side of the oil and gas industry. Now in the entire value chain, if you think about the oil and gas industry, if you have seen pictures on the internet, you must have seen a lot of huge rigs, right? You must have seen a lot of processing power plants, just like a water processing power plant. You must have seen a lot of rigs by various industrial giants, right? Now initially the thing was, if I talk about the context of what data science can bring into this industry, it can bring in safety. Let's start with that. Okay, let's start with talking about the possibilities that data science can bring into the energy industry. Possibilities. So suppose you have a huge refining power plant, or maybe some offshore structure which is lying like thousands of feet away or some miles away from the surface, within center of the ocean. You have to make sure that you follow a predictive maintenance path, right? Predictive maintenance path, right? You cannot just expect that some failure happens and you will just reverse to trying to repair the entire thing, because a failure in oil and gas industry, if anyone knows about the deep water horizon, the failure in the oil and gas industry can mean a lot of lives, and it can mean a lot of non-productive time, a lot of loss to the industry. So the initial way of approaching any failure in the industry was reactive maintenance, that we would see some sort of failure happening, then we would repair it. But now with the advent of huge computational power, we can use the sensor data which is coming to the data scientists of the energy industry. We can develop a on-stream predictive maintenance model that can suggest that, hey, within 1 hour from now, based on the historical data that I have trained my algorithm on, I can say that some failure is going to happen. Maybe 40 minutes from now, 1 hour from now, 2 hour from now. So this is a major dominant project in this industry. It can be in other industries as well. And the project that we are going to look at is something using which we will use oil production prediction. With the interest of time, I will take the questions later on. Maybe after I complete a good chunk of what I want to cover, and then we will look at the questions in the chat. So I hope that's okay.
Yes, that is absolutely fine.
Okay, thanks. So the project we are going to look at today is predicting oil production rates from the oil field data. Now, the aim behind this is, like I said, we are producing oil from a huge field of rock, and we are trying to produce as much oil as possible. Everyone knows about the oil prices, so every barrel of oil that we are producing, it is very, 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 very. It's like gold. If the oil prices are huge, so oil, we need to make sure whatever we do, we make sure we produce as much oil as possible. Now, why does a machine learning model that can forecast or predict oil production help? How can it help? It can help in the fact that we can accurately, let me write it down, accurately estimate the reserves. For example, I run a forecasting algorithm that tells me that, hey, uh, over the next 1 month or over the next 1 year, this is the oil production which is going to happen as per my machine learning model. That tells the entire economic analyst in the oil and gas industry how much cash flow we can expect in the coming times. Now, if that cash flow, if they do the break-even analysis, if that cash flow tells them that the operation of this field is going to be profitable, then they carry on with the production of the field. If that cash flow expected in the future is going to cost them some loss because they are investing too much, then they would stop producing from that field. So this is a huge opportunity for people working in the simulation space to use machine learning as a quick solving algorithm that can tell them, one, it can tell them the accurate forecast. It can guide them to what kind of oil production is expected based on what kind of operations, and it can help them decide whether they should carry on with the production in this field or not. Right. So let's start with the basic stuff in Python. If no one knows about anything about Python, you are listening to a data science video for the first time. uh, I'll try to introduce three things that are useful for very useful for data science projects as far as raw Python goes. So a bit of Python, 2 minutes, just 2 minutes. You need to know about lists. What is a list? For example, a list is a collection of numbers. For those who already know this, please bear with me. This is for those who do not know. This is a list. What is a dictionary? Dictionary is something which will store the data, but in a labeled format. A has values 1, 2, 3, and B has values 4, 5, 6. If you want to store data in some other format, let's say you want to store your name, it will be in the format of a strings, right? It will be, let's say, DV or something like that. Okay, that's as easy it is in Python. I don't think we need to go deep initially. As we go on in this session, we will figure out what is needed. We'll need a few packages. We'll need NumPy, which is it's like the calculator in Python. We'll need pandas. It's like the Microsoft Excel in Python. We'll need matplotlib, which is a way to visualize things in Python, and Seaborn, which is again better way, a fancy way of visualizing things in Python. So we will import a few libraries, and these are the few libraries that we need to import, right? So we import NumPy as NP, pandas as PD. You can import NumPy as NumPy itself. The pet name is not required. You can use your own pet name, but the data science industry, it works on conventions. So this is a standard convention. People use NumPy as NP and so on, right? Okay, now let's come to the important part, the data that we will be using in this session. Data set that we'll be using in this session. I've stored that data in my GitHub repository. And of course, I mean, for whoever who could not grasp much of it, I have all these projects stored in my GitHub. I have a huge number of projects. So if in case you want to come back and look at it, this industry interests you, feel free to have a look at it, and the link will be shared, right? So the path, I'm copying the path to the file. Okay, this is the path to the file. All right. So this is the dataset path. I've located this in, this is from open source field, which is, called the Wolf field. A field is nothing but a hectares of area underneath which the geologists have figured out that there is some oil residing there, over which some production is happening. So the dataset path is this. Let's import a data using Python pandas. Okay. So the way to do that, pd.read CSV, because it's a CSV format file, we'll just parse the dataset path. And this is our dataset. Okay. Now let's talk about what kind of data you can expect in a typical data science project and what dataset this is. This is a time series dataset. Every recording is observed on a particular day, and which is a very common data set in the manufacturing, energy, or any sort of hardware industry. Wherever sensors are located, or flow meters, or whatever, wherever recording meters are located, there is always a timestamp associated with the values which are recorded, right? Other kind of data sets can include non-time series kind of data set, where the order of sequence of elements does not matter. In this case, whatever happened on this day, and whatever happened on this day, the sequence is important. The next day happens after the first day. You cannot assume that these two dates are independent of each other. I mean, they are independent. They don't necessarily have a formula that defines that tomorrow will follow this formula, but the pattern is important. The pattern follows a particular decline that is important to us, right? So the sequence is very important as far as time series data sets are concerned, right? And one of the first things that we do in importing a time series data set from a producing field is to make sure that the date column is at the index. And the way to do that is to tell Python that, hey, can you keep the index column, which is the 0th column, as your index? Python does that. As I run it, you will see that the date column just shifted its way to the left hand side as an index. It's in the bold now. Now it's still an issue right now, because this is by default assumed to be a string in Python, because it's having underscores in it. So you have to tell Python that, can you please understand or infer the index column to be of the date time format? Because if you let it be the way it was, if you let it be a string that it was, it would not help you in plotting. It will not help you in various time series related processing steps. Almost you can subtract dates, you can figure out a date range, etc. But all that kind of processing requires Python to understand that this is a date time object. So the way to do that is to tell Python that, hey, can you parse that index to be a date time index kind of thing? Parse dates equals to true. And once you do that, all sorted. Now you have to store that in your DF. Now, the next thing which will make things easier for you is to explain what are all the columns in this data set, right? So this is the data set coming on from a typical oil and gas field. Okay. And it is, if I can annotate it, let me just use a drawing. I'll be using my mouse, so pardon me. So I'm drawing it. Okay. So, okay, it's not working. Never mind. So a typical oil and gas field is nothing but you have a huge hectare or a field of, it's almost like a farm which is isolated from the outer universe or the outer world. You barricade it, and within that field, what you do is you set up a rig, and that rig drills, and then once the hole is drilled, you start producing. And various equipments that are used in that production of oil has a stipulated name given. So for example, to start with, you must have realized that oil is flowing. That means some kind of opening must be there, some kind of choke must be there, almost like a tap through which water flows. So you can see there is a choke size feature here. This tells us how much have you opened the surface choke, It's almost as if how much of the tap you have opened to produce from. In oil and gas, you never open the choke fully. You open it, someday you will open it half, some way you will not open it too much. Pressure maintenance is very important. So that's why this column is nothing but the choke size. Okay. On stream injection hours tells you in one day, in that particular day, how many number of hours you were on production. How many breaks did you take? You cannot take a break in oil and gas field. It keeps on running throughout the day, as is the case with other fields as well. Bore water injection volume is the other column, very understandable. It is the data from other well associated with this particular well. That injector well is pushing water down the bottom hole, down the rock. It's almost like you are throwing water and flooding water into the rock, so that that water, once it goes in, it pushes oil to the surface. So that bore water injection volume is how much water you are injecting. Okay. How much injection hours you were doing on that day, how much production hours you were doing on that day. Average downhole pressure, that's important because it tells you if oil was flowing to the well, with what pressure was it flowing to the well, with what temperature was it flowing to the well, right? With what how much was your opening, how much was your diameter of the tubular through which you were producing. So all of these factors are very, very relevant for an oil and gas engineer to model something, which will be used for reserve estimation and economic analysis. So in this case, let me tell you right off the front, in this case, we will use all these other features as our inputs, and we will try to forecast or predict the bore oil volume, as you might have guessed. So our Y in this case is the thing that we want to produce is the bore oil volume. Predict is the bore oil volume. And the thing that we want to use as inputs is everything else. And that can be optimized. So basically, we are assuming that there is a physical, physical system that we are trying to model using machine learning. All the other parameters they can be used as good predictors of the oil production volume. That's our primary assumption. The algorithm we have not yet thought about, but we are assuming that all the things like the choke size, the on-stream injection hours, how much injection rate is there, how much is your pressure, temperature, all these things, if you know, you can put that thing as an input to a model, and that model can give you the oil production rates, right? So that's our assumption. Now let's look at the data set first. df.head helps you look at the first few rows of the data set, right? So you can see initially it feels like the entire data set is empty. So you can use the pandas default plotting utility df.plot, provide subplots equals to true. Okay. And it's coming up. Let me provide fig size equals to 12,4. This is the simplest way to have the first-hand visualization of your data set. 12,12. Let me increase the tallness of the figure as well. Okay. Now, the first information is pretty clear. The fact that initials were zeros, but the data set is not empty, which is good. Now, let's look at the important column, which is the Y column, bore oil volume. Okay. Where is the bore oil volume? This is the bore oil volume, the orange column. Okay. Like I said, oil and gas production always follows a particular decline. Okay. The sequence is very important, very typical of time series data sets. You cannot place the 2011 data in front of 2009 data because 2011 is later in the decline stage as compared to 2009. So the decline, when I say you can expect this to be an exponential kind of decline, initially the oil production rates, daily production rates were very high because initially it's almost like the Coca-Cola example. When you open the bottle, the flow initially is very, very fast, but slowly that flow decays down, right? So that's why similarly, 2009 is when you open the Coca-Cola bottle, and then slowly the rates kept on declining. And finally, at this stage, this forecasting model can come off to be really good because now your authorities will be asking you some questions that, hey, can you tell me what is the forecast for this particular field? If the forecast is good, then we keep on producing from this field. If the forecast is not good, then we stop right here, because we cannot waste any more money. And remember, guys, 2014 to 2018-19 was a dark period for the oil and gas industry. The economics went down terribly. So it became very, very important for everyone to realize whether it is economically viable or not. Right. All right. So these are the few columns that we have in our data set. Now, if you observe that oil production kept on declining up to 2014, and all of a sudden, if you see, if I zoom in, all of a sudden after 2014, it spiked a bit. It spiked a bit. Even the gas that was produced along with oil, that also showed a tiny spike. Now you need to have a physical understanding of why this might have happened. If there is no explanation to that, maybe machine will not be able to understand either. So the explanation rise in the top curve, the choke size. You can see the choke size has increased around the same time, which was shut in for a long time. You can see the choke size, which is the opening of the surface valves, was zero. The choke size was zero, which means the choke was closed for a long period of time. And all of a sudden it increased, the size increased as if someone opened the tap all of a sudden. And that's why the spike came up. So right off the bat, we can understand that this particular feature called the choke size feature almost has a very, very important relationship with the oil production. So whenever we get to making a machine learning model or something, this feature has to be there. And similar analysis can be done with all the other features. This is called exploratory data analysis. You need to spend a lot of time with the data. Right now, I have picked up the best features that we have from the various sensors. That's why we are seeing good signatures that correlate with the output. But normally, you will have to spend, let's say, months and months to come to the good set of features which are representative, which can be used as good inputs for the output. So right now, that's not the case. Okay, now let's move on. I have already told you about the output column, but let's store that output column name in a variable. Output column equals to bore oil volume. Okay. Now, one of the very important things is in machine learning, let's assume that we are going ahead. Let's assume that X is linearly related with Y. It's a good practice that people follow in data sciences, that it's not necessary to go for fancy models like a neural network or something if you are dealing with the data set for the first time. It's always good to start at the bottom and then keep on improving and maybe bring in more complexities. But today, let's focus on assuming that it's a linear regression problem. And right off the bat, when we assume that, we need to make sure that the multi-collinearity problem, which is a very, very typical problem in linear regression, is not existent, in at least in this data set. And one of the ways to look at the inter-feature correlation is to look at this thing, a heat map of correlations. We can use df.core. If you use df.core, it tells us how each of the two features are correlated with each other. I know this is not the best correlation magnitude to look at, but in the interest of time, let's assume we go ahead with this for an idea. Okay. And if we look at the heat map of this, again, not the best practice, but if we look at the heat map of the correlations, it will give us an idea that, hey, some features are intercorrelated with a huge magnitude. So you can either remove one of them, because why would you go with two features which are almost identical when you can just go ahead with one? You want to avoid redundancy in your data set. You want to remove all the duplicate features in your data set. Also, you want to remove all those features which are very, very highly correlated with the output as well. It's almost as if we want to prevent any data leakage as well, right? So let's look at which of these features have a huge correlation with the output feature. Okay. To save some time, I'm copying these commands. So what I'm doing here is I'm using this above data frame, df.core, and I'm filtering out for the correlation magnitudes of each feature only with the output feature. Right now, each feature's correlation with every other feature is being displayed, but let's focus on each feature's correlation with the output feature. So once we look at it, we'll see that the bore oil volume and the bore gas volume are almost 100% correlated with each other. Now, the reason behind this is gas is an associated fluid which is produced along with oil because they are flowing out from the same outlet. So if you are increasing the oil production, the associated gas production will almost always be high as well. So it's only a matter of a bit of physical calculations that you can use. If you know the gas production, you can know the oil production. If you know the oil production, you can know the gas production. So you will not use gas production as an input because that's almost as if you are cheating in your machine learning model. Your machine has to serve some value. Your model has to serve some value. And if you provide gas volume as an input to your machine learning model, your machine learning model will almost give you a zero mean squared error, almost there, 99% accurate results, etc., which is not the practical thing. Okay. So we will try to skip this particular feature. We can set a threshold that, hey, if your relation with the output feature is more than 85 or 90%, there is some leakage, there is some correlation between the output, and we don't want to use that. So we will exclude those features. Right now, let's just exclude the gas volume feature. Right? Okay. So if in case you want to look at the magnitudes of these correlations, you can use that and you can create a data frame and you can see that gas volume is almost 100% correlated with oil volume. And hence we will exclude this particular column. Again, like I said, a good practice that you can follow in other data science projects as well. Maybe there is some inherent correlation between the output and the given feature that was not conveyed to you by the domain understanding. And hence you might want to confirm with the SME that, hey, are these two duplicate features? Are these two very, very closely related with each other? If yes, then I need to skip one of these, right? So that's why we are skipping over gas volume. Okay. Now, similar algorithm you have to use for input columns as well. Okay. But right now we are seeing that the input columns are not very, very extremely interrelated with each other. So let's assume that all the other features are good. So we go ahead with input columns with this particular condition. Okay. We go with this particular condition that, hey, my input columns will be all those which are at least more than 0.2% correlated with my output and at least less than 0.9% correlated with my output. I hope this is understandable. We do not want those features which have absolutely no relationship with my output. And we also do not want those features which are almost identical to my output. We do not want to create a model which has output as the input. We don't want any kind of data leakage, right? So this condition, once we apply, we will have input columns. So the input columns that we have figured out, okay, we have these input columns. We will need downhole temperature, we will need downhole pressure, delta P of tubing, choke size. Like I said, choke size, very, very important. Water injection volume, because more you inject, more you provide the pressure, more the oil will be produced from the other well, right? On-stream hours, of course, because the number of hours you will be producing for is directly proportional to the total production obtained, right? Temperature, pressure. So basically, all in all, what we have concluded by now is whatever we did as a data scientist nicely resonates with what? Nicely resonates with the physical understanding of the domain. And which is very, very important. You need to make sure you're not shooting in the dark. You're not shooting in the dark, as in whatever you're doing must resonate with the field personnel as well. You might have to tell the story to the field people, which is again a very important thing. Your manager will ask you, hey, why did you pick up all these features? You can tell them two kind of evidences. One, the data driven evidence that, sir, this is more than 20% related and less than 90% related. That's a data driven evidence. And this is my domain based evidence that, of course, this is the proportionality and so and so. So we have concluded with the input features. Okay. Now let's create the metrics. Let's move towards ML. Till now, whatever we did was a bit about feature engineering, a bit about understanding what are the features which are important, what are the algorithms, very, very basic stuff, nothing extraordinary. Now let's move to ML. And then once we complete the entire thing, we will look at what better we could have done, right? Because of course, this is the grounded model. This is the very simplest assumption kind of model, and we might not strike gold on the first attempt, right? So X and Y we have. The first step is to define what is your X. I mean, what is your input and what is your output? Now, no matter what algorithm you use, you are trying to create a simulation of this particular thing. Y will be a function of X. Okay. This is what machine learning is, right? You are trying to create Y as a function of X. There can be some error as well, but this is the physical system you are trying to model. Now, this F, depending on what algorithm you are using, right now we are using a linear regression algorithm. So we are assuming that F is a linear model, which is MX plus C kind of thing. But if you are using a neural network, we are assuming that F is a very, very complex kind of model. So overall philosophy remains the same, but the F keeps on changing. That's machine learning, right? Now, the first thing you have to do, like every machine learning model, you have to keep one portion of your data untouched. You have to keep one portion of the data untouched, as in you will do all the modeling stuff on some part of the data, and the remainder part of the data you will use for validation. Okay. So you have, now because this is a time series data, we cannot do the random shuffling thing that we do in other machine learning algorithms. Yes, we are looking at regression right now, but I will transform the thinking to a forecasting model in just a bit. But always remember, the ideal practice in any time series modeling algorithm is to never use shuffling, because shuffling is almost equivalent to data leakage in time series problems. So if your total data set size, let's look at the total data set size. What was the total data set size? We can look at that using df.info. 3,291 rows or days of data. So we can use 3,000 as our training, 3,000 days as our training data, and 291 days as our testing data, right? We will not look at the later 291 days, and we will validate it further on. Okay. Now, one more thing that we have to be very, very cautious about is whether our data currently has outliers or not, whether it has nulls or not. Right now, this is an ideal data set, no null values. You can see everywhere it's non-null. But if in case there were some null values, you would have to interpolate. For example, if I pick up one column, let's say oil production volume, bore oil volume, okay? Bore oil volume. And if I plot it, dot plot fig size equals to 12,4. Okay. Now, if I do something like this, okay, if I use the same column, bore oil volume, and I replace a few, normally most data sets already have the null problems. Right now, because this is an idealized data set, we are not seeing nulls. But let's replace some, let's say from 2000 up to 2200. Let's replace them with, or let's say 2500. Let's replace them with np.nan. Okay, not the best way to do that, of course, but let's now visualize it. Did it happen? So you can see this, let's assume that our data originally was something like this. We had a lot of null values lying around this 2013 mark. Now, what would you do in this case? There are a few options that you can use. Normally, if you are using a non-time series example, some people go ahead with trying to use the average to fill in for the missing values. Some people follow some other tricks and technologies. But right now, the best way you can use is physics, right? You can use this kind of decline. You can model using curve fitting or whatever you can. You can model the decline in this area, because I see that this is an exponential decline. Why not fit a exponential decline model using SciPy or NumPy or whatever? Just random curve fitting that you can do in Excel as well, and use the predictions by that curve fitting to fill this particular zone. So you can use that. That would be much better. But in the interest of time, let's use something like dot interpolate. And you can see it's okay. It's not the best. I mean, it's bad way to do it, but this is something that you can do as well. Okay. So let's replace the DF output by the next thing you have to do. Once you interpolate, you have to replace the original bore oil volume by this one. Okay. Bore oil volume interpolated. So this is just an introduction to how you would handle nulls. Of course, every data column would have a different range using which you can you can follow various other ways to fill for the nans. But right now, the output column can be filled using this. It's always good to use physics wherever you can. Okay. Never keep yourself away from the domain. Okay. So we will have this. And to check for outliers, etc., and what are the columns that we need to check for, what are the columns which have a lot of outliers, you can use df.describe. A lot of people they at least type this command in their notebooks. But what is the best way to use the information given by descriptive statistics? I'll tell you one thing that I use df.describe for. So for example, I know the 75th percentile of every column, and I know the 25th percentile of every column. Follow this thumb rule that if a particular column, your minimum is very far away from 25 percentile, or your maximum is very far away from the 75th percentile, then you need to focus on that column for outlier removal. I will repeat. Pick up a column, observe if your minimum is very far away from the 25th percentile, or your maximum is very far away from the 75th percentile. If that's the case, you might have to check for outliers in that particular column. For example, average downhole pressure, the 75th percentile is 235, max is 317, looks good. But this one, the 75th percentile is 6851, max is 9316, looks bad. 25th percentile is 3972, minimum is 0, looks terrible. So this is definitely a water injection volume is definitely a column that you have to handle for outliers. Okay. But right now, in the interest of time, we are not doing that. But the way what we would do is you would either remove these outliers or maybe replace them with more representative values in the interquartile range. Okay. Let's move forward with our modeling algorithm now. One interesting problem with this data originally you can see is the range of every column is very different. The injection hours is in 0 to 25. This is in thousands. There is a column for gas, which we have removed right now, but it has millions, almost millions. So that's a problem. If you feed this data directly to the machine learning model, because of the bias in the magnitude, the machine will treat this as if the high magnitude features are very important as compared to the low magnitude features. So it's always good practice to scale it. And if you have attended some courses, you must have realized that the feature scaling makes your machine learning models convergence very fast. So it's always good to use some sort of scaling algorithm to scale your data to a particular range. And you would never scale fit a scalar on the entire data set, because that would lead to some sort of, because the scalar algorithm, what it does is scaling what it is. Let's assume that you are scaling by dividing by the max. So you have to calculate the max, right? So if you calculate the max on the entire data set, there's data leakage, because how can you know the max of unseen real world data? Maybe the max that you calculated here and the data that you found out in reality was way different. So you cannot use a scaling algorithm on the entire data set. You have to use a scaler on the training data only. That's why we did the train test split first, and now we will do the scaling. Okay, so let's do the scaling. So you can see I'm using standard scaler here. You can use min-max scaler as well, but anyway, it's fine. It's all, the idea is to chunk down every feature to a common range. Min-max scaler will bring everything to 0 to 1 range, or -1 to 1 range, but standard scaler, it brings everything to a standard normal distribution, which is centered around 0 with a standard deviation of 1. That's a fancy way of telling that everything comes to a narrow margin. Okay, so you can see I'm fitting on the training data and I'm transforming on the test data. Yes, you can transform what you fitted on the train data, but you never fit on the test data. Okay, all good. Now let's train a machine learning model. Like I said, we will start with a linear regression algorithm. Okay, we'll start with a linear regression algorithm. So from sklearn.linear model, you are importing linear regression. First, you have to tell Python that, hey, I want to use all the powers of the linear regression class. So Python arranges for that. So this is class model instantiation. So when you do that, you are creating an object of the linear regression type. Now this object will fit on the data. Right now, this is a very, very generic model. Right now, this model is not data specific. This is just telling Python that, hey, we are going to use a linear regression way of modeling. We still don't know what the data looks like. So the next step that we will do is to fit this particular generic model to the data, to make it more specific, to adapt this algorithm, which was initially very generic, to adapt it to the particular oil and gas data. So when we do that, there is some issue. Let's see what issue. Input contains nan. Yes, because we did some nan creation here, right? So let's rerun that x comma y part again. Where is it? Where is it? Okay. Just give me 1 second. I'm finding out where. Yep. Okay. Dot fill NA. Let's fill for 0. We have looked at better ways to do that, but let's just to prevent that error, let's fill with 0. Reminder, this is not something that you would ever do. So don't fill with 0. Okay. But this is just to complete our entire project. Now, if I run it, again, X train, Y train has to be run again. Again. Now, if I run it, you see now it's running. Okay. Now, you see that you are fitting on the training data X, scaled version of X, because otherwise your model would have performed badly and your model would have trained slowly. That's the two disadvantages if you do not scale your data set, and you would have lost the surety whether your model would converge to a good solution. Let's predict our Y predicted. Okay, lm.predict. Now, one thing that I want everyone to know is, given this is a linear regression algorithm, whenever you fit a linear model on the training data, I told you that this makes the model data specific, which means that the coefficients and the intercepts are now found out for this particular data. If you run the same step for some other data, the slope and the intercept will keep on changing for the particular data. That's why machine learning model, mathematically, it's a very generic thing. But when you fit on it, when you fit on a particular data, that's when it adapts to that particular data, right? Now, we will plot out our predictions along with the actual data. Okay. So we can see on the x-axis, I'm taking the timestamps. On the y-axis, I'm taking the predictions. Right now, we are plotting the actual training data and the predicted training data. And you can see it's fine. It's still fine. Very, very close. The blue lines are very close to the actual orange line, orange dots. But let's do the same thing for testing data. Let's do the same thing for testing data. And now when we plot it, you see the testing data is way apart, way off the green dots. The black is our prediction, and the green dots are the original oil rates. And you can see the predicted values are way off. And you can also see that during some timestamps, the model is predicting negative oil rates, which is laughable. In fact, it's not something that can ever happen. So that's a slap in our face that your model is not performing well. But we already knew it would not perform well. We did not handle multi-collinearity. We did not handle non-linearity as well. Maybe what if some of these features were not linearly related? For example, what if we look at df dot columns, what if in X we needed the square of the annulus pressure? What if we needed the pressure multiplied by temperature as a feature? So it's not always the case that what you are assuming is what the physical system will follow. And from experience, I can definitely tell that oil and gas subsurface systems and the physical system that you are trying to model right now, it's highly nonlinear. And that's why you are breaking the assumptions of physics. That's why your model is not performing well. Even if the test performance was good, your model would still fail in the reality. So you might have to bring in some intersection with physics, maybe some domain-based corrections on the data. We did not even check the magnitudes of all the data sets, all the features. Maybe some of the features were in negatives where they were not allowed. So you have to be in very, very close touch with the domain personnel in order to make sure what you are doing is correct. Okay. Now, if I use the same thing over a random forest, at least because right now one data-driven problem that we are facing is we are breaking the assumptions of linear regression. Okay. We are breaking the assumptions of linear regression. So why not, if we do not know how to correct for that, why not use something like a random forest, which we do not have time to understand, but just believe me that it is a model which generalizes well. It has a knack of understanding the entire crux better. If you feed data to a random forest, what random forest does is it takes in the data, it creates multiple mini models, and the final prediction is an average of all those mini models. Right now, we have the prediction from only one model, which can be bad. But random forest it's almost like you are taking the advice of all the family members. Some of them will be supporting you, some of them will be against you. But overall, whatever decision you make will be a combination of all of them. So that's the benefit of random forest. In machine learning terms, we call a model which generalizes better. So let's do that quickly and let's see whether the predictions are better in a random forest. Okay. This might possibly be the first machine learning webinar you are attending where I'm presenting towards you a model which is terribly failing. Okay. So if I plot now, if I plot the entire thing now, you can see we already came close. Again, warning, no guarantee that this will perform well in reality. But like I said, this has understood the crux better. Maybe some limitations were there, some magnitude. One benefit is we did not even have to do a lot of feature processing, just like we had to do in linear regression. We did not even use scaled version of the data. So random forest definitely is doing better in this case. But again, you still have to be very, very close in with the physics people who are working in the field. You have to check that, sir, I think in the 2009 period, there were a lot of production droppings. Can you tell me why that was happening? If that was an outlier, maybe I'll have to remove it. So we have only looked at 10% of the story. But assuming if this was a correct thing, what we would do next would be to use this black forecast. Right now, this is not a forecast, but if we modify, if we introduce some lags in our inputs, we train some forecasting algorithm. I will share a link which talks about forecasting as if it was linear regression, which is a better and easier way to understand forecasting. But if we are forecasting that this black line is our forecast for the next few months, the area under this curve, what is the unit of this black line? It is in barrels per day. And what is the unit of x-axis? Days. So if you take the area under this curve, this is barrels. So it tells you that after this red line, how many barrels are remaining from this point onwards. That's called a reserve. If you multiply the barrels which are remaining in the oil field And if you multiply that with the oil prices in the current scenario, which is, let's say, 92 Brent, if for Brent it is 92 barrels, $92 per barrel. If you multiply them, that tells you that, hey, in the future, in the next 6 months, this and this $1 million you can expect as the cash flow. And then you will do your economic analysis that, hey, I am going to forecast my investments over the next 5 months. And that tells me that my investments are going to be way off the charts as compared to the returns I'll be receiving. That tells me that, hey, I need to stop right now. And you would not use this model standalone. You would use the other physics-based simulations and maybe use a hybrid prediction for the forecast, maybe a 60-40 weighted average or something like that. But this is why we are doing that. Okay. And I hope this was a good introduction, which was a good combination, at least of what is happening in the oil industry, and how well it is connected with what machine learning workflows follow. So now I will open the floor for maybe some discussions, and maybe look at the flooded chat box that I see. Uh,
Hi, Divyanju. So there are questions in the Q&A section. We have told the people to put their questions in the Q&A section. You can start from there. If you want, I'll read out the questions and you can answer.
no, yeah, I can do that. So I'm looking at questions one by one. So
Yes.
Rajesh has asked us that, is the choke same as valves? Of course, yes, absolutely. So it's almost, you can assume it to be very similar to a tap or a valve. So a choke size, if it is more, it means you have opened the tap more, or the valve you have opened it more. And if you see the choke size to be 0, the tap is closed. Okay. Data set name, it's a wall field data. Let me paste it out in the chat for you. I will paste that. Nupur, I will share the relevant files in the chat after I answer the questions. Don't worry about that. Okay. Let me share the actual project with you in the chat box. Okay. I'm sending. Let me open the chat box first. Okay, pasting
Uh,
it here. Okay.
Till
Yeah.
then, Devanshu, I'm sorry to interrupt you.
Mhm.
Just to inform everyone, so I've started a feedback poll. Please do answer that as well. It will help us to, bring on some more sessions like this. And yes, you can continue, Devanshu. Thank you.
Okay, thanks. Yeah, so someone asked me about the oil volume and gas volume looking very, very similar. Yes, we dealt with that in the session. Like I told you, they are coming from the same valve. So gas is associated with the oil, and hence they are almost identical. They are the fluids produced off of the same valve. That's why they were looking very, very identical. So that's there. For the data set, again, I'm sharing the data in the chat. Data is copied in the chat, so you can directly import the data in the chat, right? uh, so uh, 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 may you show the above code, what kind of projects you deal with. May I understand without having them. uh, Himanshu has asked a very interesting question. Can't you step in to make understanding with data without having the domain knowledge? I mean, of course, you can do a lot of things with data, but sometimes to improve whether the data itself is correct, you might need uh, domain understanding. I mean, most of the data science teams that are created, at least in the industry, they definitely have one or two domain SMEs. They keep on attending the regular calls. You ask them whether this feature is important, whether these values are expected, whether they are representative of the physical system. So it's very important for your model to perform well. So either you do the domain reading on the background, or you connect yourself, or you involve people from the domain in your project team. Either works. Okay. So yes, I have shared the notebook. I mean, Rajesh, the threshold value of correlation features, it depends from a use case to a use case. Also depends on the company policies and the SME discussions that you have. But normally, features should not be too intercorrelated. And if you are a statistician, you might want to look at whether they are statistically significantly correlated with each other. I recently shared a mathematical background about linear regression on my LinkedIn. So please go and check that out. That explains how to handle multi-collinearity in a way better way than I could discuss today. So there are better ways to do that, right? So beginning, we can use ML instead of end of the oil reservoir. ML can be used to have a guidance, as far as I know. I mean, this will not replace any pre-existing workflow, but this will definitely be a good suggestion mark that, hey, we can use this suggestion. I mean, in fact, this was well appreciated by people from the oil industry because the simulation outputs, they take a lot of time to generate themselves, because that is dependent of partial differential equations, and to solve them, it takes a lot of time. And this is a replica of that, but it solves way faster due to computational power. Okay, so Kashish has asked whether this time series is stationary. Of course, I could not get a chance to look at that in this session. Time series forecasting can be for some other session. But of course, yeah, that's a good point to check if you are looking at it from the forecasting angle. You need to make sure stationarity is there. Chemical engineers, they definitely are very important for petroleum industry. A lot of chemical engineers are working as great data scientists in various oil and gas companies. In fact, in my last company, almost every day I would interact with people from the chemical engineering domain. So they came right from the field, working as the consultants in the data science industry. So yeah, I mean, it's always okay to ask questions about the data, like I did today. Like when I showed you this plot, I asked you why this is happening. Then I looked for some clues in the data itself. Either ask for clues from the data will confess to things, or you ask for clues from your seniors or people in the team. Okay. All right. So I think that's to select the features. Again, I would like you to refer to a LinkedIn post I shared. I will you can find that to check that on my LinkedIn. I shared about linear regression. There are, I mean, random forest. If you are using random forest algorithm, random forest has a way. I will show you. It tells you the feature importances. So I will rf dot feature importances. You can see directly. You can obtain the importance of all the features. So if some features, let's say this feature and this feature is very less important, random forest is suggesting that I do not need these features. You can use that. But right now we cannot decide purely based on this. Okay. So various algorithms have different ways to select features. Okay. Yeah. Forecasting article. I'm sharing the link. It's my attempt to, explain forecasting as if it was linear regression. But again, can find that out in LinkedIn as well. Okay, I've shared it. Splitting the data, yes. I like the answer to that by Andrew NG. He tells us that if your data size is huge, and if you can afford to have 1% as the test size, that also works. So 80-20 is not the standard benchmark. If you have million samples in your data, even 1% would mean tens of thousands of rows, right? So that's enough for testing set. So it depends on the use case to use case, right? So no. Okay, I think that's all about it for and I would definitely paste my LinkedIn as well for whoever has more questions that they could not ask today. I will share my LinkedIn in the chat. Please feel free to come up with questions. I think we are almost there at the end of this session.
Yes, we are. We have surely shared your LinkedIn profile link as well in the chat.
Okay.
But yes, you can also go ahead and share it.
Perfect. All right. Thanks.
Thank you so much, Divyanshu. Thanks a lot on behalf of Analytics Vidya as well. This has been an amazing session, and we hope to have another session with you as well. Like even the people, the attendees today would love that. So thanks a lot. It was really informative for me as well. Thank you.
Thank you, everyone. Thanks for the positive
Thanks a
feedback.
lot.
See you soon. Bye.
Thank you guys. Bye. Bye. Good night.